Okay, so for 4.3, we're going to quickly review what we've learned so far. Similar polygons are similar when the angles are congruent and the sides are proportional. I set it up like this to see that the angles are congruent and the sides are proportional. Like BC corresponds to FG. I say that this side is proportional to this side, and that works for every single side. When I ask you to set up a proportionality statement, I mean get all of the left ones, A, B, B, C, C, D, D, A, on top, and then get all the ones on the right, E, F, F, G, G, H, H, E, right there, and then I say the angles are congruent. This is what I'm talking about when I say proportionality statement. The angles are additional, but I need you to understand that you can take any piece and put it on top of its corresponding piece, and it will equal any other piece on top of any other piece, as long as it's corresponding locations. The perimeters are also corresponding to the same amount. So each one of these pieces has the same ratio, even the perimeter. Scale factor is when we're going from one to the other. So if I enlarge this, I go up by a factor of 3/2. If I reduce it, I go down by a scale of 2/3. So we talk about the scale factor of from A to B. So I'm going from A to B. That means I'm enlarging it, which means I do 5/3. If I do the scale factor from B to A, I'm going smaller, so I have to do 3/5. So if I look at this as two polygons, and I'm looking to find the missing side length, I could look at it logically and say, well, to get from 3 to 9, I had to multiply by 3. So to get from 7 to x, I have to multiply by 3 to get 21. They have to be in the same proportion. Okay, example 4.14. In your notes, list all pairs of congruent angles and write the statement of proportionality for the polygon. Well, let's start with the angles because those are easy to match up. We say that D and W match up, A and T match up, B and U, and C and V. Now at this point, I notice that angle C is 70 and angle V equals that, so I know angle V is also 70. But we'll talk about that in a bit. Now it says the proportionality statement. We pick anywhere we want to start. I chose to start with the top row at being 15. So I picked this one to be the top, and I go straight around the room. So 15, UV. There's no number there, so I just call it UV. 23, and then PW. Now I pick the side that corresponds to 15, and I get 9. I go around. I get BC, I get DC, and I get 6. So now I've got to look at these and find out the scale factor. Well, 15/9, that helps me. I can find out the scale factor from that. I reduce my fraction to get 5/3. So my scale factor is 5/3. Now when it asks me to find TW, I set up my scale factor and the variable that I'm looking for, TW. I do my cross product, I divide by 3, and I get TW equals 10. So now I look at angles. If I wanted to find the measure of PUV, here's T, here's U, here's V. If I notice that 70 and B make a CIA, they make the bucket, and the bucket adds to 180. So to find B, I have to subtract 70 from 180 to get 110. Well, B and U are equal to each other, so I say that U equals 110. Now, essential question. If two figures are similar, how do you find the length of the missing side? Write that in your own words. You can look at this page for your to kind of help you out. Scale factor, cross product with the ratio. Moving on. Transformations. This is a huge part of this. Is really 4.3. That was all review. This is 4.3. When a geometric object, point, line, polygon, doesn't matter what we're doing, is moved, rotated, reflected, some way it's changed from its previous position. So a translation is when I take a shape and nothing else has changed. All I've done is slid it across the board. It's called a slide or a glide or a translation. The point is that it doesn't move. It doesn't change at all. Now a reflection changes only in that I've flipped it over a line. Reflections always have a line of translation. Always has a line of reflection. I'm reflecting it over this line. And notice how her left hand becomes her right hand. She's been flipped over like a pancake. over that line. Now, a rotation is where we always have a point of rotation. Right here, this intersection of these two lines is the point of rotation, and it pivots like this or like this. This one says it starts here and rotates around because the arrow is pointing this way. I imagine this like my pivot foot. Here's my pivot foot, and here's my footprint. And I can move my feet as long as I want to, but I can't change my pivot foot. And that my foot has to stay in the same orientation. A dilation is when it gets bigger or smaller. Nothing else changes except the fact that I've made it bigger or smaller. I can also, while dilating, I can also move positions sometimes if my center of dilation is out of the center. So when I move stuff, when I do some sort of transformation, I start with the pre-image, and when I've moved it, I call it the image. Now, if I moved point A, I can't call it point A again. So I have to call it something different. The long bell. When I call it something different, I call it A prime. This little apostrophe here is called prime. The pre-image is A, the image is A prime. That's how you say it. The vocab. That's the lingo. If you want to sound cool, you're going to call it A prime. And it also can indicate that a transformation has taken place or how many transformations have taken place. I can put more and more exclamation points here, and I can call it a double prime. I can call it a triple prime, quadruple prime, however many I want to put on there. I can put that. And that just means I keep moving it over and over and over again. So this indicates one move, 2 moves, 3 moves, 4 moves, and so on. Now, a dilation is a transformation where the image is either larger or smaller than the pre-image. So an enlargement is when I make it bigger. A reduction is when I make it smaller. So that the pre-image, the initial start, the pre-image, that's where we started with, is bigger than the image. So overall, I'm making the image smaller. So the scale factor helps us out because when I'm looking at a dilation, I'm dilating it by a scale factor. And that scale factor is done by the image divided by the pre-image. And I'll show you what I mean by that. You can also find it by using the center of dilation. And I'll show you how to find the center of dilation and how to set up your scale factors. Right here. Sorry, phone rang. So if I look at the PRQ is my pre-image. P prime, R prime, Q prime is my image. So what I do is I connect P prime and P, and I end up here. R prime and R, and I end up here. And Q prime and Q, and I end up here. This is my center of dilation. Everything is getting bigger from this point. So my center of dilation is here, and the distance from my center of dilation to my pre-image is 2. And the center of dilation to the image is 5. So I set up my scale factors, the image divided by the pre-image. I do CP prime is 5, CP is 2, so my scale factor is 5 over 2. Now let's reverse the order. That's for an enlargement. If I'm making it smaller, I start here at the big triangle, PRQ, and I'm going to P prime, R prime, Q prime. So this is a reduction. The distance from P to C is 6, and the distance from P prime to C is 3. I find my center by connecting my pre-image and image corresponding points. P and P prime, R and R prime, Q and Q prime, and they all meet here at C. So now when I do this, I say my scale factor is the image over the pre-image, which is 3 over 6, which reduces to 1/2. Now if I were to look at this example 4.15, I've got 2 triangles, and I need to describe the dilation that moves EFG onto FDH. So here's my 2 triangles. What would be the dilation? Well, I've got this length is 10, and the length from F to H is 20. If I look at it, am I doing an enlargement or a reduction? I'm moving from the small triangle to the big triangle. Makes it an enlargement. So my scale factor is my image over pre-image. So my end result is FDH, and FH is a length of 20. So I put FH on top, FG on bottom, and I end up with 20 over 10. I cross off my zeros, and my scale factor would be 2. So I'm enlarging this by 2. Each segment will be twice as long as its original segment. So no time for questions. Let's set up an example from previous lesson. Two complementary angles have measures in the ratio 2 to 7. So remember how we talked about the angles aren't 2 degrees and 7 degrees. They're 2x degrees and 7x degrees. We got to find out what x is to be able to find out how big the angles actually are. So since they're complementary, but we know they add up to 90 degrees, I combine like terms, I divide by 9, and then I plug them back in to find out what the actual values of the angles are. 20 degrees and 70 degrees are in a ratio of 2 to 7, and 20 plus 70 makes 90. That's why that works. Now here I'm going to plot some points, A, B, and C. And then I'm going to plot P, Q, and R as well on the same graph. Now when I look at the relationship you see between the two polygons, I can tell that from the origin to here is -5. From here it's -10, so it's twice as long, twice as long, twice as long. I can see that I have some sort of a scale factor of 2. If I go from ABC and I make it bigger to PQR, it's twice as big. Now what are the area of a red triangle? Equation for area, my base is 10 and my height is 5. So I plug those in, I take half of 10 is 5, and I get 25 units. The area of the blue triangle has 10 and 20, and I get 100 units squared. So the side lengths were doubled, but the area was something different. It wasn't doubled. You'd think it would be 50 units, but it's not. It's 4 times as big. Try and find, on this essential question, what is happening. I'm doubling one, but I'm timesing by 4 to the other. Maybe there's a pattern or rule we can follow for this. And I would talk about this, pause the video if you want to do it on your own. But right now, you're going to do the scale factor squared. So if I'm tripling the side lengths, I'm going to be 9 timesing the area. So I square the scale factor. Now we're going to do this with a polygon. I graph my polygon. I graph my second point, but I don't have any. So now this is where I say if I don't tell you where the center of dilation is, you have to assume it's the origin. Now if I say it's scale factor by 2/3, I take the 2/3 and I multiply k by each coordinate. So I times it by -12 and -9. That's for p. I'm going to find p prime by multiplying these two values, and I get it to be -8 and -6. And I put my point down there. Now I do this for each one. I times by 2/3, times by 2/3 to find q prime. I times by 2/3 to end up with 6, 8. I times each by 2/3 to find -8 and 4. I complete it. I find that's my center of dilation. So if I connect S and S prime, it meets the origin. R and R prime, they all intersect the origin, which makes that my center of dilation. So I can see that I've reduced the big polygon to be the small polygon by a scale factor of 2/3. To summarize what you learned today, fill out your homework, make sure you got your notes all filled out and correct, and we'll talk more about transformations and such on another day.